Hi everyone, I'm Professor Burgasser, and in this video we're going to focus a little bit on the inclined plane. The inclined plane is one of our three simple machines along with pulleys and levers, which we're going to see later on in the course. And it's very commonly seen in all sorts of architectural and even sporting sort of environments. Of course, when you have accessibility ramps, those are inclined planes. If you're parking on a hillside, you're dealing with the inclined plane. And of course, in sports, you have sports like skiing or even biking like the Tour de France, where you have motion either down or up or both along an inclined plane with respect to the topography. So it's useful to kind of look at this, this very special case of problems in detail and see how do we go about solving for any problems that are involving inclined planes. So here's just my quick schematic of an inclined plane with a mass on it. And we're going to look at a couple cases. And the first case we're going to look at is a case where there is no friction. So our simplest case. And a question we might ask is, what is the acceleration of our block once I let it go? And hopefully it should be clear that if I let go of this block, it will just slide down the plane. But how would that motion actually take place? Well, first thing is to think about some predictions about this motion. As I just said, if I let go of the block, I would expect it to slide down the inclined part. All right. And the acceleration, I would imagine, is going to be a little bit less than g. And I can even think back at some cases where I've had things on inclined planes and look to see how they fall. And they don't just fall straight down because they are on a plane. So I would expect that the acceleration, or the magnitude of the acceleration, is going to be less than the free fall acceleration of g. We can also think of some extreme cases that, for example, when the angle that I have here for the incline is equal to 0 degrees, then that's a flat surface, and I would expect no motion whatsoever. So I would expect the acceleration to go to 0 if the angle goes to 0. And similarly, if the angle goes to 90 degrees, right, in that case it's a perfectly straight vertical cliff, I would expect the thing to actually fall in free fall. So maybe I should make this a less than equal to g, and for the special case where the angle is 90 degrees, a should go to g. And that actually starts to give us some clues about what the solution of this problem is going to be. But let's actually go through our regular physics protocols and draw a force diagram, break down the components, and see if we can solve for the motion based on the way we've drawn this. So let's draw our schematic for our block. All right, and I'm going to draw it at its angle here. And again, we have this angle theta at which the inclined plane is set up. Let's think about the forces acting on this block. This is near the surface of the Earth and it has mass. So we're going to have a weight component, mg. This block is in contact with the inclined plane, so there's going to be a normal force pushing outwards. But since there's no friction, I don't have to draw a friction component here. Now, there may be other forces such as viscosity or air resistance. I've chosen not to include those, and so this is really a complete force diagram. But notice that the forces are not aligned along a rectangular coordinate system, so I have to choose a rectangular coordinate system that's sort of best suited for this. Now, it turns out for motion along these planes, it's often convenient to choose a rectangular coordinate system such that the coordinates are aligned with the plane itself. That's not aligned with the gravitational vector, but it separates the motion to motion along the plane and motion perpendicular to the plane. As we'll see, it's a little easier to solve that because we can make some constraints on that, in particular the perpendicular motion. So let's choose a coordinate system that is tilted with respect to that inclined plane. So this axis, which I'm going to call the x-axis, and I'm actually going to point that in the downward direction, is going to be equal to theta with respect to our normal horizontal. We can very easily break down our force components here. The normal force is very simple because it's aligned with our y vector. The gravity component, now I have to figure out how do I break up the components. Now the original gravity vector is sort of pointed in this direction. So there's going to be a component along positive x and a component along negative y. And they're both going to start with mg. And I just have to decide what are my trigonometric identities. Now, as we've done before, there's many ways of doing this. One of the ways I like to think about is what happens when the angle goes to 0. In that case, the inclined plane tilts down, so my x component is along the surface, my y component is perpendicular surface, and the gravity vector would just be pointing along the y-axis. So when theta is 0, I better have all of my gravity vector along the negative y-axis. And the trigonometric function that gives us a 1 when theta equals 0 is cosine. So that means that this component is cosine theta, and of course this component is the opposite, sine theta. Right. You can also do this by drawing a triangle and figuring out the opposite, hypotenuse, adjacent, for example. But I like to think in terms of these extreme cases. All right, so that's our force diagram. So now we can just write down the components of force along these vectors. Let's do the y-coordinate first. All right. So we've got the sum of forces along the y direction is equal to n minus mg cosine theta. And that's equal to the mass of the block times its y acceleration. And our x hat component, sum of forces along the x direction, is just equal to mg sine theta alone, and that's mass times its a acceleration. Now, we can actually make another constraint to this problem because we have 3 unknowns, the normal force and the 2 components of acceleration. Again, by tilting these axes, I can note that the block is just going to slide along the inclined plane. It's not going to jump off or fall into the plane. So the acceleration along the y direction, or perpendicular to the surface, is probably going to be 0. And that gives us an expression for our normal force, which is mg cosine theta. Now, that's not particularly useful for this problem, but will be useful when we look at the next step when we add friction. Looking at our second equation, we can see that we can cancel out our masses, and so that tells us that our acceleration along this axis is g times sine theta. And in fact, that's the number that we were looking for, was the acceleration of the block down the inclined plane. Now, we can go back and check our predictions, all right? It is sliding in the direction which I've drawn down the inclined plane. Of course, if I had chosen to put my x direction the other way, I should end up with a negative number. So the way I've drawn this, this is the right answer, going down the inclined plane. The amplitude of this is less than g as long as theta is not equal to 90 degrees. When theta is 90 degrees, you get exactly g, and that's a prediction I made for this extreme case. And also, when I have theta equals 0 degrees, or a flat plane, sine of 0 goes to 0, so I'd get no acceleration at all. So everything fits with our predictions, and it's consistent with our force diagram. So let's consider the next step in complexity. Let's add a little friction to this problem and ask the question, what angle of this inclined plane is the maximum angle at which this block will stay put? So this is really a statics problem, and it's a statics problem that involves friction and varying this angle. So again, we can think about some of the predictions of our answers. All right. For example, I would suspect that as we increase the coefficient of friction, then I can tilt this angle to a higher degree. So the higher the mu, the higher or the larger of an angle, that's going to be the critical angle. And then we can maybe put some constraints about what that angle can be. Certainly the angle is probably going to be greater than 0 degrees because that's just a flat plane, and that's fine without any friction at all. We saw that in the last problem. But it's probably also going to be less than 90 degrees because at that point the inclined plane is vertically straight up and down, and you wouldn't actually have any more contact with the surface then, so the object would just fall down. So that gives a fairly wide range for the angles, but at least lets us check for some solutions that might be wrong. All right, and so let's go ahead and see if we can approach this problem by writing down the force diagrams and see if we can realize some of these predictions. So I'm going to go ahead and draw again my schematic for my mass here. And as in the last problem, it's got a weight, mg. It's got a contact force, which is the normal force. And in this case, since we have friction acting on the problem, it's going to have a friction force as well. And that friction force is going to act in the direction opposite of which the block would move, which would be downwards. And so we'd expect this friction force to point in this direction. And since we're looking for the maximum angle, we're looking for the case where the friction force is at its maximum value, and that's when it's equal to mu times the normal force. All right, now like the last problem, it's convenient to choose a coordinate system in which we are tilted with respect to the inclined plane, because that sets some constraints on the y direction of motion, although since it's a statics problem, there's actually no motion at all in this problem. So let's go ahead and draw these coordinate axes the same way I did in the last problem. I'm going to have an x component pointing along the plane, a y component pointing perpendicular to the plane, and now we can break up our forces just as we did before. The normal force pointing away from the surface. We have our components for gravity. Those haven't changed, mg sine theta and mg cosine theta. And now we have our friction force, and fortunately that's aligned with the surface of the plane, and so that's just going to point in a negative x hat direction. That's mu n. All right, so now we got our force components. We can start to write down our equations of motion in the assumption that there's no net acceleration on this block. So the sum of the forces in the x direction are equal to mg sine theta minus mu n, and that's equal to 0 because we have no net acceleration. The sum of our forces in the y direction are n minus mg cosine theta, and that's also equal to 0. And so that allows us to solve for our normal force, just as we did in the last problem. And we can plug that number in here to get an expression for for solving this expression. So we can write that down, mg sine theta minus mu times mg cosine theta, theta is equal to 0. And we can now cancel out a couple of the terms here. Both m and g go away. And if I just rearrange, if I subtract mu cosine, or sorry, add mu cosine theta on both sides, and then divide by cosine theta, what I get is the tangent of theta, sine over cosine, is equal to mu. And this is the critical angle. Okay? So now let's go back and look and see how this solution matches up with our predictions. Well, it's very clear that as mu increases, tangent of theta going to a larger value requires a larger angle. And so that's consistent with the angle getting higher for higher values of mu. The smallest that this can be, where the mu is equal to 0, where you have no friction, that's going to be a case where theta is also equal to 0. So that's consistent with our expectations. And we can't get to a mu high enough in which this is going to be 90 degrees. In fact, when theta is equal to 90 degrees, sine of theta is 1, cosine theta is 0, so you have actually infinite. So only if you have infinite coefficient of friction could you have an angle of 90 degrees. Most of the time we're restricted to just 1 or 2 as the maximum values. So we can also look at what we've learned from our solution. We were able to cancel out the mg terms in both cases, so that means that our solution for the critical angle doesn't depend on the mass or the gravity. So it's sometimes often useful to write down what we've learned, and that's the critical angle is independent of the mass or the gravity. So it doesn't matter what mass I put on this inclined plane, I'm still going to have the same critical angle, the same steep angle in which something will slide or not slide. And it also means that this would apply not just on Earth, but also on the Moon or Mars. So this seems to be an intrinsic property, this angle, that's related directly to the coefficient of friction between whatever two objects I have as the inclined plane and our mass. So let's go one more step in complexity and add a pulley to this problem. Here's the setup. We've got our mass on the inclined plane, but this case is now connected to another mass that's suspended off the back end of the inclined plane through a pulley. And so we can ask a whole bunch of different questions for this, but let's ask a statics problem again and ask what range of masses for M2 will keep this system as a stationary system, will keep it from moving. All right, so again, we want to think about the motion a little bit and make some predictions. All right, so if we're thinking about the range of masses, we can think that there's actually two kind of things that could happen One is that if the mass is not big enough, then the block will just slide down. So the low mass range keeps M1 from sliding down. The opposite case is if I have too heavy of a mass here, too large of a mass here, that will be enough to actually pull mass 1 up. And so the high mass range keeps M1 from sliding up. Okay? And then there should be some other interesting behaviors that, for example, if the coefficient of friction, if mu is equal to 0, then we would expect to have really kind of no angle at which this would be possible. Because in that case, there's nothing sort of holding the system together, and so this thing should just automatically slide. Another possibility is if theta is equal to 90 degrees, which case we just have essentially an Atwood machine, a pulley with two masses sliding down, that can only be balanced if M1 is equal to M2. And there's a few other things that we can think about this motion, but let's start from there, and then let's start analyzing the force diagram to see if we can understand what's actually happening. Now we've got two objects here, so we have to draw a force diagram for each of those objects. Let's start with our initial first mass, and we're going to have some familiar components here, although now we've separated out the different masses. So we've got our weight for our mass, we've got our normal force over the contact, we've got friction acting, and this is actually an interesting point because we can have friction acting that way if the block is sliding down. But of course in my second case it could be that the block is sliding up, in which case friction may be acting in the opposite direction. So in fact either of these directions are ones that we're going to have to consider. We also have a connection point with a string, so there's going to be a tension force that connects that string to the object. Now let's go ahead and break down the components of this particular force diagram much the same way we've been doing. And that's because we have most of our forces aligned with this tilted rectangular coordinate system. So most of our forces are going to be exactly the same. We've got our normal force, we've got a coefficient of friction which may point up or down. We've got our normal gravity components, mg cosine theta, mg sine theta, and now we've added a tension force. So we've got quite a busy force diagram in this case. And now we've also got the second object that we've got to worry about. All right, that is mass number 2. But fortunately its force diagram is much simpler because all we have is its weight pointing down, and its only contact with the rest of the system is through the string, through this tension force, T. Okay, so let's go ahead and take a step back. In this case, for the second mass, we can just use a simple one-dimensional coordinate system because that's the only direction in which we have forces acting. All right, so now let's start to write down the equations of motion because we're looking for a case where the system is stationary, and then we are really looking at a statics problem. So it's just the sum of the forces are equal to 0 along each of the components for each of the objects. So let's actually start with object number 2. In this case, we only have forces along the y direction, so we can go ahead and write those down. T minus mg, and that's equal to 0 because for stationary we've got no net acceleration. And so that tells us immediately that the tension along the string is just, and make sure that's m2, is just m2 times g, which is great. Gets rid of one of our unknowns, which is the tension. Let's switch over to object number 1 again. If I start with the forces along the y-coordinates for this particular object, that's going to be n minus mg cosine theta. And that's the only two forces, and again that's equal to 0, so we have the familiar result that the normal force is mg cosine theta. And now where it gets interesting is of course the motion along the inclined plane. We've got several forces to write down here. If we choose positive to be in the down the inclined plane direction, We've got mg sine theta pointing down. We've got tension pointing back up the inclined plane. And now we've got a choice because we can either have a positive or negative mu times n, or mu times mg cosine theta, positive or negative because it's going to depend on whether the object, this mass is so heavy it wants to slide down, or this mass is so heavy it's actually pulling it up. We have a choice here. This is what gives us our range for allowable masses. But in the end, all of this is going to equal to 0. And let's make sure we're clear that this is mass 1. So I got to make sure I label my masses here because we're going to actually look to see what this looks like for the range of masses. So let's go ahead and add in our tension relation. So m1g sine theta minus m2g plus or minus mu m1g cosine theta is equal to 0. The g's and all of these terms cancel, so our problem is going to be independent of the actual acceleration due to gravity. And we can just do a little bit of a rearrangement here to set aside m2, so I'm going to add that to this side. That's going to equal to m1 times the combination sine theta, and then plus or minus mu cosine theta. And that is our expression for the allowable range of masses, or at least the masses that satisfy the case where neither component is accelerating. So now that we have our solution, let's make sure that it makes sense and sort of check it with our predictions. So let's take the case of, for example, when mu is equal to 0, when we have no friction. Now we originally predicted in that case there would be no angle which there's a balance. But in fact, if mu is equal to 0, let's actually write this down. Mu equals 0. This means that m2 is equal to m1 sine theta. So in fact, there is an angle in which you'd have a balance. And if we think about it more carefully, that kind of makes sense because if you have an equal amount of weight here and an equal amount of the force acting in this direction, which was just the weight times sine theta, then that should actually balance out. In fact, that's exactly the mass balance that we would expect, right? Because that gives us our sine theta. So in fact, we've corrected a misconception. Even though mu goes to 0, we can have a balance point. And that balance point is just based on the components of weight, either vertically here or along the direction of the inclined plane. So we can also look at cases where, let's say, we want to look at when theta is very small. Okay? In that case, we're going to have the sine theta term become very, very small. And if we subtract mu cosine theta, we're going to get a negative mass, which seems kind of strange. But what it's really telling us is that if the angle is so small, then the mass 1 is very heavy, and it provides lots of sort of normal force on the surface, and it's providing a lot of friction surface. And so this mass 2 can be very large and still not really pull the object over, right? Whereas if I do the plus sign, I can get a very large factor for mass 1. In that case, you're going to need a lot mass to actually start to pull this thing off to the right side. All right, so for theta small, you get a much wider range. And for mu large, all right, we have a large value. That means that the range is bigger, all right, because this plus minus factor is going to give us a larger range for our values. Now we can also evaluate some example numbers just to see what the sort of expressions look like. So let's say I take an angle of 45 degrees and a mu value of 0.33, which is typical for wood-on-wood contact. In that case then, m2 is equal to m1 times 0.71, which is the sine of 45 degrees, plus or minus a third of 0.71, which is equal to 0.23. All right, and if we write this out in terms of the actual numbers, this is going to be a range of 0.48 m1 is less than m2 is less than 0.94 m1. All right, so that's an example of the range of masses in which this object would be stationary. So there's lots of ways of playing with this one solution, but of course it all comes basically from coming back from our force diagrams and then reevaluating our predictions that we made ahead of time.